Okay, it's my pleasure to introduce Sarah Peluze from IAS at Princeton. And she will talk about an asymptotic version of the prime power conjecture for perfect different sets. Thank you, Sarah.
All right, so thank you for the invitation to speak. So first I'll tell you what perfect different sets are. So a perfect different set is a subset of some cyclic group such that every non-zero element of that cyclic group can be written uniquely as the difference of two elements of your set. So subset D of a cyclic group is a perfect different set if every non-zero A can be written uniquely as A equals D1 minus D2 for D1 and D2 elements of D. So we care a lot about perfect different sets in additive number theory because they give examples of kind of maximally large seed-on sets. A perfect different set are seed-on sets, which means that they have no non-trivial additive quadruples. That means that if A, B, C, and D are elements of D, and A plus B equals C plus D, then A and B have to be the same as C and D. And we care a lot about like how large seed-on sets can be and like what they look like. In particular, we care about, when do these perfect different sets exist? So there's some easy constraints. So by simple counting argument, if a perfect different set exists in the integers mod m, then we must have that m is of the form n squared plus n plus 1 for some integer n. And then this situation, the size of D is n plus 1. And when this happens, we say that n is the order of the perfect different set D. So order isn't the same as cardinality here. And this terminology mirrors the terminology associated to finite projective planes. And there's a good reason for that, which is that any perfect different set gives rise to a finite projective plane. So any perfect different set D of order n gives rise to a projective plane of order n. By taking the points to just be all of the integers mod n squared plus n plus 1, and the lines to be translates, to be the set of all translates of D. So sets of the form A plus D for A in the integers mod n squared plus n plus 1. So in addition to being of interest in additive number theory for being seed-on sets, perfect different sets are also of great interest in finite geometry, design theory, and coding theory. So the kind of most basic fundamental question about these perfect difference sets is when do they exist. So more precisely, for which n do perfect difference sets of order n exist. So Singer in 1938 constructed examples of perfect difference sets of all prime power orders. So here's his construction. So let's say we want a perfect difference set of order Q for Q some prime power. So what Singer did is take zeta to be a primitive root of fq cubed. Then he took the difference set D to be all powers, or all m, such that zeta to the m can be written as a plus b zeta for some non-zero, both a and b, along with 0. And that zeta is a root of an irreducible cubic, basically gives you the perfect difference set property. So Singer constructed perfect difference sets of all prime power orders, and it's an old conjecture that these are the only orders for which perfect difference sets exist. And this is known as the prime power conjecture. So it says that n is the order of a perfect difference set if and only if n is a prime power. So Singer didn't conjecture this himself. He conjectured something different but related that I'll mention in a bit. And the earliest reference I can find to this conjecture is in a paper of Marshall Hall in 1947. But he makes it sound like people had been conjecturing it for kind of a few years earlier. So Singer gives one direction of this conjecture. So the open question is, are there any perfect difference sets of non-prime power order? So what's known about this conjecture? Gordon actually very recently has verified it computationally for all n below 20 billion. And it's actually more generally conjectured that all finite projective planes have prime power order. So this construction I showed you, where you take the points to be all the integers mod n squared plus n plus 1, and the lines to be translated to the difference set. These give you a finite projective plane, but the projective planes that you get by doing this with a perfect difference set are far from all of them. They're just the projective planes that are known as cyclic projective planes. So there's a lot more projective planes, and people more generally think these only exist with prime power order. And Singer conjectured in the same paper that he constructed these perfect difference sets in, that all perfect difference sets of prime power order basically look like the ones he constructed. So Singer conjectured that all perfect difference sets prime power order look like, so maybe they're like some translation or dilation, the things I wrote above, look like the example from above. Okay, so this means that if you take together the prime power conjecture and Singer's conjecture, you get a complete classification or a complete conjectured classification of all perfect difference sets. So the strongest results known towards the prime power conjecture, besides kind of checking computationally up really high, are results that kind of remove certain congruence classes from possibly being orders of perfect difference sets. So one example of such a result is due to Bruck and Reiser. It's actually more general than perfect difference sets. It's actually about all finite projective planes. So it says that if n is congruent to 1 or 2 mod 4 and is the order of a finite projective plane, then n must be able to be written as the sum of two squares. So the density of integers that can be written as sum of two squares is like 1 over square root log n. So it says that most integers that are 1 or 2 mod 4 can't be the order of a perfect difference set. So some other results that remove congruence classes from possibly being perfect difference sets are results of Jung, Nicol, and Vetter. From, I think, 1984. That says if n is multiple of 2 and is the order of a perfect difference set, then either n equals 2 or 4 or 8 divides n. And there's also a congruence restriction mod 9 due to Wilbrink. Says that if n is a multiple of 3, is the order of a perfect difference set, then either n equals 3 or 9 divides n. So this is actually it for kind of results in the theory of perfect difference sets that remove like a positive density of orders of perfect difference sets. And note that kind of these all taken together don't tell you that the density of possible orders of perfect difference sets in the integers is 0. So the result I'll be telling you about today is that yes, the density of orders of perfect difference sets in the integers is 0, and it actually has the order predicted by the prime power conjecture. So the number of little n below big N, such that n is the order of a perfect difference set is 1 plus the low of 1 times n over log n, which is the number of prime powers asymptotically below n. So some remarks about this. So actually have an explicit expression for this little one term. It is e to minus some constant times log n divided by log n. I didn't try very hard to optimize this, but it is something explicit. And so you can ask, like, could I prove such a result more generally for orders of projective planes? And the answer is no, I can't, at least not with like my methods. It uses some things that are really specific to perfect difference sets and not more general, like finite projective planes. And in general, things seem to be much harder. Okay, I guess they must be like at least as hard to say something about like all finite projective planes. But as an example of this, so we know the prime power conjecture for n up to 20 billion, but we still don't know if there's a finite projective plane of order 12. So saying things about general projective planes is a lot harder. So are there any questions before I start talking about the proof? Okay, now tell you about the proof. Or maybe I should call this section proof ingredients. So I don't prove all that much really new about perfect difference sets. What I really rely on are some kind of fairly old results on perfect difference sets that are about 70 years old, that say if n is the order of a perfect difference set, then certain relations between the prime factors of n squared plus n plus 1 and n must hold. So then the prime factors of n and squared plus n plus 1 must satisfy certain relationships. Oops. And so then, once you apply these results, this turns the problem of bounding the number of non-prime power orders of perfect difference sets into a problem in analytic number theory. So the first of these results that I use is a theorem of Mann from, I think, 1952. So it says that if we let n not be a perfect square and be the order of a perfect difference set. Then if P is a prime dividing n, and Q is a prime dividing n squared plus n plus 1, then P must be a quadratic residue modulo Q. Okay, so this is a very strong condition, and we'll get a lot of mileage out of this theorem, but it's actually not enough to prove a true like asymptotic for the number of orders of a perfect difference set, because it turns out to be useless when n squared plus n plus 1 is a prime that's 1 mod 4. So when n squared plus n plus 1 is 1 mod 4 and a prime, this condition in Mann's theorem actually ends up being empty. And this is just a consequence of quadratic reciprocity. So if P is an odd prime dividing n, then we know that n squared plus n plus 1, well, it's just going to be 1 mod P, so it's definitely a square. But then whenever n squared plus n plus 1 is 1 mod 4, quadratic reciprocity will tell us that P then also has to be a quadratic residue mod n squared plus n plus 1. So every prime dividing n, or every odd prime dividing n, is a quadratic residue mod n squared plus n plus 1 in this case. And so Mann's theorem just doesn't give us anything. And we have to deal with this case, though, because by the Bateman-Horn conjecture, we expect that n squared plus n plus 1 is a prime that's 1 mod 4, at least a constant times n over log n of the time. So do have to deal with this case. Okay, and the key to dealing with this case is to not look at squares, but to look at fourth powers. I show, and it ends up not being too difficult of a thing to show using standard things in the theory of perfect difference sets, that if, say, Q equal to n squared plus n plus 1 is a prime that's 1 mod 4, and n is the order of a perfect difference set, then any prime P dividing n must be a quartic residue. Modulo Q, which is n squared plus n plus 1. And the way this is proved is kind of similar to the proof of Mann's theorem, and it uses something called the theory of multipliers of perfect difference sets. I won't say more about it because I want to talk about the number theory. So now, with Mann's theorem and this lemma in hand, it should kind of not be surprising that the number of orders non-prime power orders of perfect difference sets is really small. So for a typical n, or n squared plus n plus 1, you expect like one of these to have enough prime factors that these conditions should very rarely hold. So the problem with turning this like heuristic into like an actual proof is that n and n squared plus n plus 1 aren't independent, right? Like n squared plus n plus 1 depends on n. And so the key idea is a way to remove this dependence is to note that the conditions imposed by Mann's theorem and this lemma are strong enough that one can afford to lose a little by using the union bound. To remove some of the dependence of the prime factors of n squared plus n plus 1 on some small prime factors of n. Okay, so this is a little vague. I'll show you how it like actually works in practice. So I'll tell you about the proof. Okay, so we want to bound.
Sorry, Sarah.
Oh yeah.
What's the union bound? What's the union bound? Okay.
So it's, I'll write it down. So if we want to bound like the cardinality of some set, that's just the union of some other sets, then kind of the crudest thing we can do is just sum over I and take the number of things in each set.
Okay, it's just that.
So what I end up doing is writing the number of orders of perfect difference sets as a union of some other sets in such a way where like doing this crude thing doesn't actually lose you that much. So the way the proof goes is, so we want to bound number for the size of set S of n, or S of n, which is just going to be the set of non-prime power orders of perfect difference sets below big N. Order of a perfect difference set. Since Singer's construction gives us the lower bound for this asymptotic in the main theorem. And to do this, we split up into 3 cases depending on the number of prime factors of n squared plus n plus 1. So split into 3 cases. So the first case is when n squared plus n plus 1 has at least 3 prime factors. Second is n squared plus n plus 1 is the product of 2 primes. The last one is the last remaining case when n squared plus n plus 1 is prime. And as the number of prime factors of n squared plus n plus 1 decreases, kind of the difficulty and the involvedness of estimating the contribution to S from each of these sets increases. So first I'll talk about the case when n squared plus n plus 1 has at least 3 prime factors. Okay, so okay, so for a typical such n, n will be divisible by 2 relatively small primes, neither of which is equal to 3. So equal to like n to the 1 over 100, such that P1 and P2 divide n, and these are distinct primes. And the contribution of the n such that n doesn't have these 2 small prime factors, and n is also the order of a perfect difference set, can be bounded in a similar way to what I'm about to describe for this case. So for typical such n, we have 2 small prime factors dividing n. And then for all n such that n squared plus n plus 1 has at least 3 prime factors, we also know that n squared plus n plus 1 will be divisible by some prime below n to the 2/3. So for all such n, there exists some q below n to the 2/3, such that q divides n squared plus n plus 1. So now we split up the n we want to estimate based on P1 and P2 and q. So it suffices to bound size of number of n that are the order of a perfect difference set, such that P1 and P2 divide n, and q divides n squared plus n plus 1. And so here I've used the union bound. And now using Mann's theorem, can transform this condition that n is order of perfect difference set into some quadratic residue condition. So this is bounded above by the sum over the same thing. But now I need to count the number of n below big N that's divisible by P1 times P2. And that n squared plus n plus 1 is divisible by q. And such that if q divides, let's say q prime divides n squared plus n plus 1, then P1 and P2 must be quadratic residues mod q prime. And if P, we go called P prime, divides n, then P prime must be a quadratic residue modulo q. So now the key thing to note is that we're estimating the size of this set is a sieve problem of dimension 5/4, which crucially is greater than 1. Because so this condition that any prime dividing n squared plus n plus 1 must be such that P1 and P2 are both quadratic residues modulo that prime. So this removes 3/4 of a congruence class modulo each prime on average. And this condition that any prime dividing n must be a quadratic residue modulo q. Oops, I didn't write that. So this condition removes half of a congruence class on average. And it's not hard to show that they end up removing different congruence classes, even if P happens to be playing the role of Q and some other, or actually no. So n and n squared plus n plus 1 are relatively prime, so these are different, always different primes. So since this is a civ problem dimension 5/4, you can use just standard upper bound civ to get that this is bounded above by sum over the same things. And this condition that neither P1 nor P2 are 3 is like a technical thing having to do with like which primes actually have roots of n squared plus n plus 1. So we get that using upper bound civ, the size of each one of these sets is like n divided by P1, P2, and Q times log n to the 5/4 times some Euler product, some partial Euler product depending on P1, P2, and Q. But it turns out not too hard to show that this kind of mysterious Euler product is very small on average. Like it's typically like bounded by a constant. And then kind of summing over P1, P2, and Q, we just lose some powers of log. But this ends up being fine because we've already saved like more than one power of log n. So this gives us n over log n to the 5/4 times log n, some bounded power. Right. So to recap, we used the union bound up here to remove some of the dependence of the prime factors of n squared plus n plus 1 on the prime factors of n. But we kind of gained so much by using the sieve here, using the conditions from Mann's theorem, that we saved like more than a power of log n. And this is more than enough to counteract what we lost by using the union bound, which was just what we got from summing over 1 over P1, P2 times Q. So we just lose like a power of log n. Okay, so this is what happens in the case that you have at least 3 prime factors of n squared plus n plus 1. So now when n squared plus n plus 1 is the product of 2 prime factors, this splits into 3 subcases, maybe actually 4. So when, let's say Q1 is the smaller of the 2 prime factors. So when Q1 is below into the 2/3, the same argument above applies. And when, let's say the smallest prime factor is between n to the 2/3 and some n divided by some fairly large power of log, like log n to the 100, need to do something slightly more delicate, but kind of a variant of the above argument works. But then when Q1 can range from all the way up to n divided by the square root of log n. You have to be even more delicate. Which I won't have time to tell you. I'll say it involves breaking up such n that are the product of 2 primes and have their smaller prime factor below n divided by square root log n, you break such n up based on their smallest k prime factors, for k being some parameter tending to infinity, like very slowly. Like I end up having to take it to be like log log log, or log 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 of n, and then kind of bounding each of these sets separately using a sieve argument. And it's from this step that I get this like kind of hideous thing with 11 logs, because you end up needing to take k to be like pretty small to make it work. And then finally, when the smaller of the two primes is really close to n itself, kind of none of these arguments using Mann's theorem work anymore. So what I have to do is to actually forget the condition that n is the order of a perfect difference set, and just show that the number of little n below big N, such that n squared plus n plus 1 is product of two primes, and G1 is bigger than n divided by square root log n, is just smaller than n divided by log n to the 3/2. So the way I do this is just using an enveloping sieve argument. And this is fairly standard as far as the actual enveloping sieve argument itself goes. But as one of the inputs, I need an asymptotic count. With power saving error term. For the number of points, or integer points, on the hyperboloid y squared minus 4xz equals -3, with various size and congruence restrictions. On x, y, and z. And the way I end up needing to prove this is by kind of modifying an old argument of Hooley that he used to count the number of divisors of values of quadratic polynomials. Okay, so this covers all the cases when n squared plus n plus 1 is the product of two primes. So the last case is when n squared plus n plus 1 is a prime. So the case when n squared plus n plus 1 is a prime that's 3 mod 4 is easy. And it's easy for the same reason that the case when n squared plus n plus 1 is a prime that's 1 mod 4 is hard, which is basically quadratic reciprocity. So quadratic reciprocity implies that in this case, using Mann's theorem, if n is the order of a perfect difference set, then any odd prime dividing n must be 1 mod 4. So bounding the number of n that are the orders of a perfect difference set such that n squared plus n plus 1 is a prime that's 3 mod 4 is like bounding the number of n such that n squared plus n plus 1 is a prime, and n is only divisible by primes that are 1 mod 4. And this is also a sieve problem of dimension 3/2. So you easily beat n over log n. So now we're finally in the hardest case when n squared plus n plus 1 is 1 mod 4. So the idea is to, kind of like I mentioned for one of the cases when n squared plus n plus 1 is the product of 2 primes, we split such n up based on the smallest k prime factors of n, which we'll call p1 up to pk. So we will want to estimate and okay, we'll also assume that these are all also smaller than like log n. So we'll want to estimate for each of these k tuples of primes the number of n that are the order of a perfect difference set, such that n squared plus n plus 1 is prime that's 1 mod 4, and each p1 up to pk are the smallest k prime factors of n. Okay, so by using the lemma on this quartic residue condition, this says that you actually want to estimate the number of little n below big N, such that n squared plus n plus 1 is prime plus 1 mod 4, and p1 up to pk are the smallest prime factors of n. And finally, that all of the pi's are quartic residues modulo n squared plus n plus 1. Okay, so by using some one of the incarnations of the quartic reciprocity law, we get that this, same as bounding, same conditions on n, but now the quartic residue condition turns into that n squared plus n plus 1 can be written as a sum of 2 squares with various congruence restrictions. On y that depend on all of the pi's. So you can estimate the size of each of these sets now that you've transformed it into this writing as a sum of 2 squares with a congruence condition. Using the Selberg sieve, can estimate this as long as we have another point count for a different hyperboloid than the one before. As long as we have the count with power saving error term for the number of points on the hyperboloid 16x squared plus 4y squared minus c squared equals 3 with some size and congruence restrictions. On x, y, and z, depending on these primes pi. And I also prove such a count by modifying this argument of Hooley that I mentioned earlier, but it's a lot more complicated in this situation just because this is a not as nice hyperboloid. Okay, so I think I'm done.
Thank you, Sarah.
Thank you.
So we have time for questions, so this is time.
Just, excuse me, very basic question. I was just wondering whether the definition of perfect different set was rigid or not. You assume that you can have only one solution to a minus b equal to 0. And if you assume that maybe you have one exception.
So, oh, sorry.
I mean, if you allow one exception in your definition.
So if you allow one exception, I don't think you can prove kind of like any of this stuff. Like you really need this like 100% rigidity. Because it's used a lot in some of these results about multipliers that I mentioned earlier. You can relax the definition in other ways that I guess are still similarly rigid. Like you can say, oh, everything can be written as the difference of two things in like exactly 5 ways. And then these are also things that people have studied and can say a lot about. But if you say like, oh, it can be written as the difference of two things in like up to 5 ways, then I don't think you can prove much.
I was just wondering whether if you allow one exception, m equal a minus b and equal a prime minus b prime, I mean, I'm wondering whether it cannot happen.
Oh, like whether
maybe
any of these things exist?
Allowing one exception rules out the case. That's what I'm wondering, in fact. I don't know. It's just a question.
So I haven't thought about this, like either whether such things exist.
Either you have several times several solutions. Yeah. Okay. Thank you.
So I also have a question. So you said that the worst part of the error term comes from the middle case, where n squared plus n plus 1 can have 2 primes, right?
Yeah.
But so do you think it's possible? So because it happens because in the case you said was the hardest one, the last one, you have this quartic residue argument, right?
Yeah.
Do you think it's possible to like somehow enhance the lemma so that it simplifies the proof on the middle case, or it is that it is?
Oh, so also, okay, I guess I didn't say the bad, the thing with the 11 logs also comes out in this last case because you have to do the splitting up thing.
I see. So yeah, there's no reason to run away from it. Okay. Thanks. So you also have, but that means that you also have to divide according to the number of primes. Oh, so sorry, to the size of the primes dividing.
No.
Yeah,
I also need the primes to be small so that basically so that the product of all of them is like reasonably small, that I can like estimate things well.
Okay.
So it's like this like double restriction that I need like infinitely many of them, or some number of them going to infinity really slowly, but I also need them all to be like really small.
Okay.
And I need them to be like triple logarithmically in like both. And that's where like this 6 logs thing comes from.
Okay.
Could you scroll back to the 2 prime factor part of the argument, please?
Yeah.
First of all, I thought it was a really nice talk, so thank you.
Well, thanks.
So if I understood correctly, you have this kind of complicated argument that led to the poor dependence when Q is on this range between n over log n to the 100 and n over root log n.
Yeah.
And then if Q1 is a bit bigger than n over root log n, then things get easier.
Yeah.
So what's the significance of n over root log n as a threshold here?
So I could have taken anything between n over like log n squared minus epsilon and and just n.
Mm-hmm.
So you end up saving like in this kind of enveloping sieve thing, you end up saving, if you want to count the number of such n that are such that n squared plus n plus 1 is the product of 2 primes, Q1 and Q2 between let's say x to the 1/2 and x. I think what I end up getting is that you save like log x squared or something.
Mm-hmm.
So I think you save like x divided by log x squared. So then so what do I do? So I guess I take this to be like n times square root log n. And that's how I get the log n to the 3/2. But you can't take x to be like too large, or you don't actually end up doing better than n over log n here. And I think, yeah, the limit is like x is like n times log n squared.
Okay. It seems as though a kind of range for one of the prime factors between n and n over any power of a log is a very small range. So you'd expect to save something from there. And also, of course, to save something from the fact that you have 2 prime factors of n squared plus n plus 1. But I guess the numerology is different, maybe. Thank you.
Okay. So, okay, more questions? No?
No.
No. In this case, thank you very much again, Sarah. What's a very nice talk.
And very nice result.
Yeah.
Yeah.
Was-
See you guys next week.
Thanks for the invitation to speak.
I was happy to hear about this finite geometry set, because I've recently bought this card game called Double. Do you know it?
No.
So it's this card game where the cards are round, and in each card you have 8 different symbols, and there are so these are basically projective lines in finite geometry. So this is a geometry where you have 8 points in each line, and each line crosses the other one in only 1 point. So that's the game. You have in each pair of cards, you have exactly one drawing which is the same. So the game is to find it